Hello and welcome to lesson number 3 in Unit 2, Quadratic Functions, Forms and Transformations in our grade 11 University College Math class. This is Transformations Part 2, Translations of Functions. So in our last lesson we went over the first set of transformations which dealt with the a value, which contributes to the way your graph looks by either stretching it or compressing it, or potentially reflecting it across the x-axis. So that's really just about the shape of your parabola. Today's lesson on transformations will deal with how do we move our parabola left or right or up and down. And again, we're basing this on the vertex form of a quadratic. So let's jump right in to translations of functions. We're going to start with a horizontal translation. And again, as I've already said, this doesn't impact the shape, this impacts where your parabola shows up. So we're going to look at three graphs, three graphs to sort of set up what this transformation looks like, or what this translation looks like, which is also a transformation. First one we're going to graph here is y equals x squared, and we're going to fill out a table of values. We're going to follow that with y equals x minus 5 all squared. And finally, we're going to look at y equals x plus 7 all squared. So first things first, let's start by completing these tables of values. So we do this by substituting in, and I've provided you here with the x values we're going to substitute. People always ask this, which x values do I pick? You can pick any old x value you want. I tend to pick points. If I'm not sure what my graph is going to look like, I tend to pick points sort of clustered around the origin, 0, 0, just as a way of ensuring that the stuff that I'm going to be putting on the that I'm putting in the table will be graphable. So let's start by substituting -2 into y equals x squared. So -2 squared is going to give me 4. 1 squared is going to give me 1. Or sorry, -1 squared rather is going to give me 1. 0 will give me 0, and then 1, and then 4 again. Now this is a fairly common parent function graph. We should be fairly familiar with these at this point. The vertex, however, the lowest point is going to be 0. 0, 0. So let's get this on the graph. Starts at 0, 0. From the vertex, we go out 1 and up 1 on both sides. Back to the vertex, out 2 and up 2 squared, which is 4. That's all we've been given here in our table. So I'm going to graph this in, kind of make it look a little bit curvy. Get some arrows on there. Because we're going to be putting three graphs on here, I'm going to hold off on the labeling a little bit, as well as the labeling of the x and y axis. We're going to leave that for now. Okay, so there's our parent function. As we know, our domain is going to be wide open. There's no x values that we can't use. So we would say here the set of all x such that x is an element of real numbers. No limits. Whoops. No limits. Oh, pardon me. And then we're going to talk about the range. The range, as we know, is limited by our vertex. Our vertex is 0, 0. So we start by saying the set of all y such that y is an element of real numbers where y is going to be greater than, since our parabola opens up, or equal to, since we get all the way to 0 and we close it up. So there's our domain, range, table of values, vertex, and graph for our parent function. Let's jump to the second example. So the second example, again, I've provided you with the appropriate input values here, so save ourselves a little bit of time, but we're going to substitute 3 in here. Now, I'm not going to do all these calculations longhand written out, but consider we're subtracting 3 from 5, and we are going to be squaring it. 3 minus 5 will give us -2, which squared gives us 4. If we substitute 4 in there, 4 minus 5 is -1, which squared gives me 1. If we substitute a 0 in here, or rather a 5 in here, 5 minus 5 gives us 0, which squared gives us 0. By now we can see the pattern. It will also be 1 and 4 for these next two. So our vertex, of course, represents our lowest point, so or our highest point, maybe. Let's start by graphing this. So that's going to be 3, 4. 1, 2, 3, and then 1, 2, 3, 4. It's up here. Whoops, that's right. 3, 4. Next one is 4, 1. Next one is 5, 0. 6, 1, and 7, 4. And same thing here. We'll sketch this now, keeping it fairly curvy. Up we go. Put some arrows on there. And again, I'm going to hold off on labeling everything right now. We can see that our vertex is our lowest point. Our lowest point is going to be 5, 0. And let's fill out the domain and range. Again, domain for any parabola, any non-word problem parabola, I guess, would be the set of all x, such that x is an element of real numbers, wide open, no limits. Our range, however, limited by our vertex. We know that the lowest point that we're going to reach is going to be 0. And we would then write set of all y, such that y is an element of real numbers, where y is greater than or equal to 0. And again, greater than because our parabola is going to open up. So there we go, our second example all worked through. Let's do the third and final example. Again, we're going to start by doing our table of values by substituting these points in. So that'll be -9 plus 7 all squared. That's going to give us a -2, and -2 squared gives us 4. -8 if we pop it in here, -8 if we pop it in, we end up with -1 plus 7, which is -8 plus 7 gives us -1, which squared gives us 1. Now we can start to see the pattern here happening again. So there we go. Let's start with some graphing here. So we're going to start at -9 and 4. 1, 2, 3, 4. And -8 and 1. -7, 0. And there's the rest of our pattern. Let's graph it out a bit, keeping it curvy. Get some arrows on there. And now I'm going to go in and throw on these labels since that's our last graph. So our x-intercept here is going to be -7, 0. Our vertex in our parent function, of course, 0, 0. And in our second example, that was 5, 0. Okie doke. Let's finish this up. Our vertex of course, here is our lowest point, and that's going to be -7 and 0. We are going to write down our domain, which is wide open, set of all x, such that x is an element of real numbers, no limits, and our range, set of all y, such that y is an element of real numbers. Our lowest point, of course, being 0, and opening up means greater than or equal to. So there we go. We have our first set of graphs kind of rocked through here. And now we're going to do a little bit of summarizing. So what we'll notice with our parent function, of course, is that it goes through 0, 0. It hasn't moved left or right. The next parabola that we graphed, y equals x minus 5, interestingly enough, our parabola has shifted to the right. So this one has shifted this one 5 units. And our third example, rather, despite being x plus 7, has shifted all the way 7 units to the left, which is going to be -7. So what we've articulated here is that whenever you have an x value inside when you have a number inside the bracket with the x, this constitutes a horizontal translation. And the direction is the opposite of the sign that appears. And it's because our parent function, and I'll just write that out up here, recall that our parent function is f of x equals a x minus h all squared plus k. What dictates the fact that it's the opposite of how it appears is the fact that we have a negative value inside this bracket as we've been provided it. So if we were to substitute in, for example, oops, that's a highlighter. If we were to substitute in -7, it would actually look like an x plus 7, despite being a negative. So that's the explanation as to why the direction that we move our parabola is the opposite of how it appears. Let's do a little summarizing here. So the graph of f at x equals x minus h all squared has its vertex at h, 0, whatever it happens to be. So it is a horizontal translation, and that's going to be h units, whatever our h value is, and if it appears negative, it is actually a positive shift, and that will be to the right. Similarly, if we have a graph of f at x equals x plus h all squared, it has a vertex also at h0. Now again, that h value is negative, but the h itself doesn't have a sign assigned to it, but it is still a horizontal translation, and it is going to be h units to the left, since it will in fact be a negative number. So what we know is that when our h value is less than 0, so when our h value is negative, our parabola moves to the left, and when our h value is larger than 0, which is an actual positive number that appears negative, it is going to be a horizontal shift to the right. So there is our first part, or I guess the first part of this lesson on translations. This is the horizontal translations. In part 2, we're going to look at vertical translations. So we'll see you in part 2.